Okay.
Okay, I think we will get started.
Yes.
Okay, because we are sorry about that. We take a little time because this is what problem we are facing is we hope while working with the Shane, we're trying to secure one place, but what happening is the meeting room is so, we have to continuously find a room for our talk. Thank you all for coming here today. I know also welcome the people from the Zoom. This actually is the second time we have this UD Mobility Forum. Today we are very happy to have Professor Chandra. I know it's a little bit come on. Yeah. So Professor Chandra right now is a full professor at Computer and Information Science. I know we normally just call ourselves computer science, yeah, but officially it's a Computer and Information Science department. Chandra is very well known in the computer vision area. So for some of you probably know that he recently just been appointed as the general chair for CVPR 2026. That will be a very big visible position for University of Delaware, and also congratulations for your appointment. But before he joined the UD, he was a research scientist at NASA and have getting a lot of awards. I'm not going to mention that. He's also very actively not just developing algorithms. His lab is in 210 Smith Hall.
Right. 212.
212 Smith Hall. I encourage you, if you haven't been visit them, take a look of his visit his lab if you are at our UD campus. So he most recently he's just getting another large, I would say a large grant from Army Research Office that is a focus on those multi-model using drones, cameras, and then to detect the hidden targets. So that and this technology, I was told that this technology has been used in the real field. So in some of the real, deployed in Europe and some other places. So also, Professor Chandra received our department's inaugural Outstanding Faculty Research Award last year. Yeah, congratulations to him again. So without further ado, we will welcome Professor Chandra to share with us his work on the 3D point cloud, which is a very hot topic these days. Okay, go ahead.
Thank you so much, Wei-Song. Appreciate it. Sure. So I would like to first thank Wei-Song for having me over here. Shing, thank you. So this topic is very exciting, and I hope some of you students get excited to work in this area. Some of researchers collaborate with us. Like Wei-Song said, we are in 212. Feel free to come visit us at any time. So I'm going to talk about 3D point cloud analysis. The main talk is going to be representation and some novel idea that is used to represent 3D points. When I say 3D points, I mean 3D point cloud. I'm proudly saying that this work is my idea. Some of the students helped me implementing them. Some 10, 15 years ago, I worked with a geography researcher, and I was talking to them, and they said, all the papers we work with the students, how about we have, we forget our student days, how about we have our own research, our own, theme going on. And then I said, wait, that's a great idea. So I just started to work on my own, and I came up with a representation scheme, and I did have students help me. So please do ask me questions at any time. We're going to talk some interesting stuff that I'm hoping that you'll be excited about. So 3D point cloud analysis is interesting. As you know, our phones have the 3D sensors. The automobile systems have it in the autonomous vehicles.
You are sharing your whole screen, and people can have to see you.
Okay.
Let me see.
I just need to share the right screen.
Oh, do you mind open the video so people can see you talk?
Right, absolutely. Yeah. Is this good?
Okay. Can you see him now? Okay. I know this will make it good. Okay. Yeah.
So the theme of today is point clouds. As we know, the amount of 3D data is only going to expand. Right now, you have a 3D sensor that you're probably holding on your iPhones. This was unimagined some time ago. In fact, when I did my PhD, which was on 3D stuff, I had to travel to Urbana-Champaign to get a scanner of a face, for example. I just can't believe it can happen real time. So there is need for new algorithms. We're going to talk about some motivation behind why these point clouds are important. And then we're going to talk about some new representation called Saint. I'll tell you the full form of Saint. And some of the projects that my student undertook and whatnot. So again, this is interactive, so feel free to ask questions. I just don't want to lose any audience. So let's just ask questions if you have any. So what is a 3D point cloud? Point cloud is nothing but a set of points representing the object in 3D space. And it's Euclidean space, so pretty much it's XYZ points that is defining the shape of the object. This is a classic teapot with XYZ. You can see that they're not connected, and I'll talk about all those representations in a second. But you can see that there is no texture, but you perceive the depth. So pretty much 3D is what that is. A lot of interesting 3D scanners out there. On the left, you are seeing the classic LiDAR is on the time travel based. Then there is depth sensors that we're all aware of, Connect, for example. On the top, you're seeing a CT scan. That's a 3D scanner too. It's a volumetric 3D scanner. On the bottom, you're seeing the iPhone, which actually have the depth sensor as well as LiDAR. The depth sensor, so on the right, you're seeing a depth map, typically of a depth sensor. The middle one on the right is volumetric. That's the output of a CT scan. And the top is the mesh. So let's take the depth map. Depth map basically is a 2.5D. So you take the, let's say, depth sensor, Connect, for example, it projects IR, invisible structure, onto the object. And there is another camera that uses that structure. And in that angle, it records 3D. But then it's giving you 2.5D, really. It's not giving you the complete 360 degree, right? So depth maps are usually the frontal parallel 2.5D. The middle one on the right is the volumetric. That's the typical CT scanners, where, if you take this room, if you can, this is a cube, each voxel is either occupied or unoccupied, and that's the result of a CT scan. So that's the CT scan based representation. Then comes mesh, which could be LiDAR based, probably, where you're getting the full view. You're getting the full view, but you can also see that. Sure, no problem.
The screen sharing has some issues. We need to.
The screen is not coming up.
Yeah, they can show. See this.
Okay. So
Works now.
they're not able to see this one.
Yeah, you can have one.
Okay, so maybe I just should do.
The worst case, we can do this.
That is okay. No.
Can you slide the move?
Okay. Can the Zoom see the full screen? No.
No.
Let's
Here is the.
Okay, so stop screen. This is the share. And I'm picking this, but I should pick this,
Yeah.
maybe.
Yes.
Yeah. Now it's
Yeah,
okay.
yeah.
Okay, I just didn't.
Ah,
Thank you so much.
good. Thank you, guys.
So, okay, so that's the teapot that I have shown. And we are on to the next slide on point clouds. And we are saying that the left LiDAR gives you the view in latitude, longitude. Depth sensor gives 2.5D frontal parallel. And the CT actually gives volumetric. So if you think of this entire volume being a CT scanned, each area is turned on or off, each voxel basically. So different representations. On the right, you're seeing volumetric, depth map, maybe the back of the bunny is not seen. And the mesh is a certain scanner probably, but then you're seeing that there's connection information. That means each vertex is connected and that connection is given to you, vertex pointed to vertexes. So So that's interesting. So we have these interesting scheme of mesh representations. One thing that is common that you're seeing in all of them is you can actually see the shape. So if I'm transmitting a shape from one A to B, if someone taps it, you can actually see the shape. To some extent, it doesn't make sense, right? So, well, someone can actually take the shape and find out that it's a bunny. It's complete encroachment. So the current representations really does not, they didn't think about it because we worked on 3D, but we never thought 3D will be so usable by like regular people. We like the shape, but the fact that you can easily tell that it's a bunny doesn't really help us in the long run. So you can, so all this, so right side, you're seeing the representations, whether it's mesh, volumetric, or depth map. Okay, so we're going to see what we can do about it. In the middle, you're seeing point clouds. Essentially, these are points, XYZs. So you can get these XYZs from mesh or volumetric or depth map, right? Except that the depth map is giving you frontal parallel. You can also get the entire view by rotating the sensor. Okay, so that's the idea why a new representation is important. The existing representations is revealing the shape, is giving away the shape. So the use cases of this point cloud are many. Autonomous vehicles, which is the primary theme of this forum. AR, VR is on the synthesis side. On the other side of this 3D points, there is synthesis of data where you're actually seeing the visual information of the 3D space, metaverse, though it's not doing well now, but the whole idea is in future, people are communicating in a 3D space with 3D interactions. Healthcare is the biggest application. It's there even before this big data of 3D started, because we all remember having CTs present even early days, right? So if you think about it, nature is 3D. So you can see that fundamentally the sensors are going to move in that 3D direction because we are doing recognition in 3D. The vehicles are driving in 3D and whatnot, right? So there is no question that 3D is important. So the idea of this 3D that is used in different situations are many. One is the medical community, where you can actually use it for planning, simulation. You can get a 3D data taken, and you can visualize it pre-operative decisions and then post-operative analysis using this 3D data. You can do 3D printing, which is really untapped market. You can actually, you need 3D to 3D print, and you can actually go on to analyze the situation in a 3D printed model much better than even a visualization, right? You can hold it. The construction industry is the biggest market out there that's untapped, where it's projected that there is going to be a 7.7% increase in the compound annual growth from now to 2030. The global 3D reconstruction technology market is expected to reach around 2 billion by end of 2030. So that's the level of research that we're going to see on 3D analysis. One example that is pretty recent in March 2022 is a woman had the disease called microtia, whose one of the ears was damaged. And that was replaced using the other ear by basically shape matching and 3D printing the model ahead of the surgery. Great application, right? So because obviously the ears have to match, so the perfect application for a 3D shape analysis and printing and actually implementing in real life. Another example, this is also pretty recent. In fact, it happened this year that a baby was born in Poland who has a missing skull area where the brain was exposed. Even in this case, they used 3D data to print the skull, okay, and did a lot of analysis on 3D points to come up with a strategy to do the operation on the baby to actually fill up the gap. Okay, so this is actually becoming much more real than it's not a textbook anymore. It's actually being done. Obviously, the theme of today is autonomous vehicle. The autonomous vehicle has 3 systems: perception system, planning system, control system. The perception system is responsible for environmental sensing. You're talking cameras atop the vehicle that would look at the environment real time, find out the objects in front, behind, on the side, whether it's pedestrians, vehicles, and try to identify them. And then basically real-time feedback for the planning and control systems, right? So the biggest research directions in this is between 2D versus 3D. Obviously, we all want 3D, but 3D sometimes is slower. So people do use some 2D analysis and kind of reverse project it onto the 3D. This is an example of a LiDAR data. That's how it looks like. You are seeing the environmental sensed by a LiDAR. Just to give a little bit of a background of a LiDAR, it's a active sensor. That means it's doing actively. It's not like, okay, it's not a passive sensor in the sense that it's doing one scan and be done with it. So it's constantly doing this laser beams. It's based on the velocity of the laser beam that's hitting the point and coming back, and you're traveling, you're computing the distance. So typical resolution is 360 degrees horizontal, 0.3 degree dynamic resolution, and then 27 degree with 0.4 degree dynamic resolution vertical. Okay, so that's the example of a LiDAR. So our goal, again, the entire shape is revealed. Our goal is really to represent this data, not just as points, but something beyond that. Because really, what's the goal? If the goal is to identify those objects in the scene, we don't necessarily need to just use XYZ raw points. We could actually change the representation and then work on our algorithms in that representation. Okay, so this is the kind of stuff that you would like to see in this 3D point analysis. On the bottom row, you are seeing the bounding boxes on different objects localized on the LiDAR data that was sensed in the top row, right? So the top row is the LiDAR, and the bottom row is where you're actually showing where the objects are, and the colors represent what the objects are. So that's really, and this is coming from a CVPR 22 paper. So that's the goal. But what's the first thing that's to notice is that that LiDAR is not dense everywhere, right? It's unstructured. So that's the biggest problem in this LiDAR and 3D point analysis is that, you need algorithms to work at both sparse and dense levels of points. Okay, so obviously it's more dense closer to the camera and less dense away. So all in all, we would like that encryption to happen. Since there is going to be multiple frames per second, you want compression. Okay, you want also all of this to be lightweighted, isn't it? So we don't want heavy weighted systems like big computers needed to run these, mobile computability. Also, I just said about variable density. You want something to work on density that's variable. Let's look at this picture, okay? Someone is making the picture of Spock. So in the top row, on the first image, left to right, Spock is being built, right? So let's think about it. 3D data that you're seeing at the end, right? Sculptures did it all the time. 50 to 100 years ago is when it kind of started, the sculpting. It's a human form of expression. So that means something is in their mind that they're bringing it out, but not bringing it out in the way that you look at the data. That means they're not doing symmetry. For example, they don't do left cheek and then right cheek. They do it in their own way, right? They take a clay, they kind of do depress and whatnot at different places in their own way. So that means maybe we are not doing, so we try to understand everything by symmetry and other things that we are comfortable with. Probably that's bottom-up approach. We see the Spock and we are seeing symmetry, but when it's being built, that's not the way it's being built. So what we are trying to say here is two things. One, maybe we should not follow traditional approaches to represent data, okay? Two, maybe you don't need to go to the right row last Spock data to find out that it's Spock. Maybe you can just stop at the top row third picture, okay? So what are those features that are interesting? In fact, we are right now in the hunt to find a good sculptor to actually track their hand movement and then reverse engineer it to actually find out where the features need to be used to identify a particular human being or particular animal, whatever the object is. So what I'm saying here is called task-driven approach. So the task-driven here is making a face here. uh, rather than universal approach where features are being just understood by like changes of curvature and stuff like that. We need to actually find out what are the important features that are out there to identify that particular object. So task-driven versus generality. The next is, of course, we want this to be semi-supervised or unsupervised. So that means we would rather not have training done. Okay. Any questions about anything? So let's see what happens next. So we came up with a representation called SaintRep, and it's surface aggregation in topology. So why I like that word, say surface aggregation, is that when this sculpture is doing these different dips, if you think each thumbprint is a surface element, the way these elements are dipped are different. They are not next to each other. There is no locality there. Okay, so the topology is not shape-based. Topology is based on where this person is creating the features, really, right? Do you agree? Like if they're making an elephant, the way they make the elephant, that's the topology. Not the topology that you're seeing things smooth, because our eyes are closed. Our eyes like to look at things locally, right? I'm looking at this chair, but I'm not looking at that chair at the same time. But then if this chair and that chair together tells me that this is a hall, I would rather do that. Do you agree? I just need to either learn or find a good representation. So that's the key of this work, surface representation, surface aggregation, and that's used in representation. And the topology used is, I like to call it wild, but it's not smooth. It's not neighborhood based. Okay, little bit of understanding of human fallacies. Well, we look at this picture and then say there's an elephant, then there's a horse, there's a dog, there's a cat, mouse. It's not true, right? I just want to bring out that fallacy in us. We don't even know if there is a horse painting and the rest is all like just background, right? So just to bring out that fallacy in us, that we are not perfect. This picture, obviously you probably saw it, but the inside triangle looks brighter. It's a fallacy, that's not true. And this picture could be visualized as frontal, parallel, or side looking, right? It's human fallacy. So all we are trying to say is that all these XYZ points, machines don't need to follow us because we have our own deficiencies. So let's look at what the representation I'm talking about here is. So we all know what a sphere is. Sphere has points, right? Each point is XYZ. A given center, a given radius can have different XYZs. So if you think of this room has a lot of XYZ, let's not even look at shape, a lot of XYZ, I can just bring about some 100 spheres and represent each of the point using a sphere. Because spheres has XYZs, the room has XYZs, I just have to match them and I can convert this entire room into a bunch of spheres. You agree? In fact, I can also do ellipsoids, but spheres is easier. Why not spheres? Because if it's a plane, I just use a large radius. If it's curvature, less radius, right? So a chase is flat out, okay, fine, put a bigger balloon. So I look at points as points, and I just want to represent that points. So that means if there's a car, I just put in balloons inside and I record where they are touching the car. Balloons are spheres, right? In this case. Do you agree then I can get all the points out? The touching points are the latitude, longitude, the centers. All you need is center and latitude, longitude to create the XYZ back, isn't it? Okay, any questions? So the representation is nothing but that. You just have a lot of spheres go into this 3D world, touch all the XYZ points you want to model, and record those center, radius of the sphere, and the touch points. Okay. And those places where it's touching is the topology I'm talking about. So that's the topology representation is that. So
those spheres you can use a different size.
right.
If you
Right.
there's nothing here, you can make a very big
Right.
one, make a
Right.
small one.
Right. We did all right. Right. We did. Yeah. Thanks. Those experiments is exactly what we've done. So different objects. Okay. I don't know if the Zoom can see the video, but Different objects are nothing but different spheres, isn't it? Different shape of the sphere and different placement of the center. And those colors represent the touch points, okay? Okay, so if that's the case,
Are you playing a video?
I just played, I think it may not, oh, it didn't even come here, I just played it.
No, even here.
Oh, it didn't even, oh, it didn't even come here. Okay, just give me a second.
There's a button there. You move the mouse, I can see there's a button shows the video. You probably click it.
Sorry, so should I click something here for us to show? Okay, so that's okay, don't worry about it. I just do some,
Yeah, I saw a video button just now.
maybe I just,
Here? This is a video.
so that's okay. So I just, okay, 1 second. First, I just need to get this video on the screen if it works. So this one I played. No,
That's the screen. Oh, we can't see it.
right. And that to come onto the screen, do I need to move it around? Yeah, this one. Right.
Oh.
Why I have to do it?
Oh, then you
Why I
need to
have to
show
do
the
it.
whole. Then let's don't do that because that's gonna be.
Okay, so let's just do it here, okay?
Yeah.
Huh?
But it's okay. He doesn't want to show it to us. For the Zoom guys, they can click it themselves later, right?
So all I'm
Wow.
saying is these spheres, different centers are representing different objects. Now, can you tell what shape it's representing? Yes, no? No. Okay, you just see spheres. It could be face, it could be horse. Okay, I'll just share the screen. Sorry, I just.
Okay, now we're back.
Sure.
Can you see it? Yes. Yes. Okay.
Thanks. So essentially, for each point is assigned to a sphere regardless of the local shape. By the way, if I put a big sphere here, I can get that blackboard and this blackboard, right? So my topology is completely changed. So my way of putting things together is different than, okay, since things are next to each other, they need to be together, right? So I just want us to understand that the sphere is not representing like things that are close by, but it could represent this and this and this and this, though they don't belong to the same object. My idea is to create XYZ points, that's all. Okay, isn't that what sculpture does? Just that, right? So our goal is to be able to get the point reconstructed back from the corresponding sphere, center, and radius. We all know we can get it back. Polar angles. Any point can be obtained from a certain center and sphere radius, so we can model any surface point. Is it lossy or lossless? It's lossy, right? Okay, we are missing points, but then if you use more spheres, you get more accuracy. Okay, cool. So the algorithm is simple. It's Ransack style sphere fitting to generate sphere radii and corresponding 2D array representing polar angles. Contact map is what that lat long array is. I'll show you the example of that. We just output those sparse contact points. That's what that Saint is. The benefit is compression. All that humongous data are now a bunch of spheres. Now, maybe I just need 30 spheres to recognize something or 20 spheres, but it's scalable. That's the best part. It's scalable. If I have a lightweight mobile phone, then I would just use 10 spheres. It's important that it's encrypted. better classification. I will show you the results on better classification. I just want to make sure. So I think I have 30 more minutes, right? So, and then it's multi-scale, like I said, it's remote VR. Don't you think if you're doing VR of these, you just store the radii and occupancy map? That's a better way to do it than this entire 3D data. Okay, so again, the conventional representation exposes the data. You can randomize it and encrypt it. So that's how the occupancy map looks like. Actually, I said occupancy, later it's being used in volumetric data representation, and then I converted it to contact map. So contact map is nothing but the latitude longitude array where it's touching the point. Okay, so like I said, I showed the sphere that's touching like dashboard. Those points, latitude, longitude, are on, the rest are 0. So it's a sparse representation. And the best part is your data is like, so that's your data. Okay. Now what Wei Song was saying is, okay, what type of spheres can be used? You can do non-random progressive. That means just start with a big sphere, small, like that, and then just store all of them. There is, I don't know if I haven't heard before this work, but there is something called sphere packing. Kepler is known to actually have done that. A lot of us know Kepler for, I guess, the systems that Kepler's laws and things that I've studied when I was a kid. But now there's actually something that he came up with, it's sphere configuration. So if given a space, what is the best arrangement of spheres to occupy the space? He came up with it. It actually is a hexagonal pattern. I don't know if you've been to, I'm sure in China, India too, they sell fruits. They have a certain arrangement of fruits.
Yeah.
So, right. And that there's a reason for that, which I had no idea, by the way. So that's the reason. So that's the sphere packing, actually. They can actually put more oranges, apparently. So these spheres, we use that packing to represent the shape. So the A is a regular grid, B is that hexagonal grid, C is just an example showing this sphere packing. D is original data. It's a LiDAR. It's a connect data, I think, of an indoor scene. E is using regular pattern of oranges or spheres. F is actually using sphere packing, hexagonal. Interesting, right? You have less error. By the E and F, of course, are errors between the constructed and the original. Okay, you see more errors in E than F. Right? Makes sense, right? Though that may not make a difference for classification, but definitely for reconstruction, it does help. Okay, so what Wei Song was saying about progressive, the last one is the progressive. That means a big sphere, smaller sphere, like that. Versus the middle one is the random, just drop in spheres. Don't control it. Don't let whatever radius it is ransack. Okay. They also come to be the same, except I think the progressive will work better for a single object. So this one is single, but if you have multiple objects like this room, chairs, tables, then, but progressive is a very good way to do it for face, for example. Okay, any questions about anything? Our representation is unsupervised. It's a reconstruction framework. Additional annotations are not needed. It allows the knowledge of reconstruction process if we actually learn it. We were actually going to learn these placement of spheres. It can be progressive, random, all that, but what about we know exactly where to put spheres for the best reconstruction, right? That goes back to the sculpting. So we were actually thinking of actually following the hand movements of a sculptor to then identify where to put those spheres, right? So that's something that, so that means, so there's a volume of clay that Spock is being made. You can reverse engineer it and you can put the spheres at those places to actually represent Saint in the best possible way. But right now we're using randomized. So we pick 4 points, we estimate the sphere, and then we find out the inliers. We find out all the other points, which ones are inlier, which were outlier, and we do the next one. So we do 1,000 iterations and then we take up the second. Right? Yeah, so for I number of spheres, get the best sphere using ransack, remove sphere center, and then just record that theta phi rho. And so your vector is, we also keep XYZ just for classification purposes, but you can actually throw it if you're using reconstruction, right? So sphere center radius theta phi rho, that's enough to take a scene of XYZ, convert that into Saint. Then what? A lot of points now become nothing but number of spheres times, if you say center and radius is floating point, 4 bytes. So one center, XYZ, one radius, one floating point, total 4. 4 times however many bytes you use for floating point, 2 bytes sometimes, long is 4 bytes. That reduces your entire data to minimum size. So each occupancy is also for sparse, so we could just use a linked list or something nice for that. But it's basically you just want IJ values of occupancy, right? IJ as to where it's on. You guys agree? Where is it? Yeah, correct.
Yeah, so if I understand that is the reconstruction is like a compression technique to the point cloud.
Right.
So I'm curious if for some application like you use LAN in AV, compare with the original point cloud.
Right.
After you do this compression, well, they give you the same performance.
Right. That this is lossy, and I'll show you the result. Right. But the classification actually improves. So if you're interested, see, because all these XYZ, you have a good point. I just want to add on saying that all these XYZ points, if the final answer is to localize the object, to classify the object, well, it's getting better. But if you're doing a surgery, right, you don't want classification, you actually want real XYZ points.
Yes.
Then you increase the sphere for more accuracy. But I do have errors to show. Yes. Good. So that's why it's scalable in the sense, yeah. So all in all, it's fitting the points, calculate these occupancy or contact maps, convert to sparse format. Let's look at some results. How about dental? We actually went to UPenn dental school and actually got this data. That's a mold, right? So they CT scanned it or so, I think we are given, and we did a Saint. The first one shows the teeth. The second one shows the points of Saint. Third one shows points overlaid. It's that accurate, basically. Okay. But of course, we should come up with numbers based on certain application. So that's the car. Now, this is showing the process of fitting. Okay. So those are all patches of each sphere. And you can see the points are being picked up by spheres. Okay. Feel free to ask questions. Each round is basically, I used to play a game called Digger when I was little. So it used to just eat things. So each sphere comes and eats away the points. That's the way I look at it. Takes away the points until there are. So you can see that there are removed points as to each sphere is removing points, representing them into the Saint format. So total is 50 spheres. Okay. One more car. You can see large curvature is more planar. Okay. If you do that, the top row shows the original cars, the bottom row shows the Saint cars, basically. Okay. I will also talk about compression, okay? Because end of the day, how is the data less? There is 3D data out there, 105 subjects in various poses and expressions. Total so many number of scans. We went, because face is easier, right? So if there's an expression, are we keeping the expression after Saint? Right? So one example is to see how many spheres you need for us human people with human vision, find out that it's a sphere. Maybe the top row, third face, that's 50 spheres. But if you want more data, you're going all the way to 250. Okay. Again, I have a video. I know I may not be able to show to the Zoom community, but oh, you can see it here. That's the original face. Okay.
You know,
Hmm?
we have been trying to do the face expression detection for babies.
Sure.
And found out that there's not much, work has been there because of there's no such a
Delicate expression.
yeah, the data, and also for babies, very.
There is no data.
It's
Right.
very difficult.
Right.
So I wonder if this approach,
Right.
with the self,
Right.
is unsupervised, so maybe pretty helpful.
Yes, definitely. Yeah. We should talk, yeah.
Okay. Cool.
So that, yes. So that's the original. That's a saint. Can't tell the difference, okay?
This face reminded me that you guys are watching a movie, recently there's a movie called, yeah, I watched it last week. It's a movie, there's a one guy, exactly
That,
I get a guy was made it by. It's called Ant-Man. Ant-Man and Wasp. That's I think it's David, some of your guys.
so that reminds me of 3D movie industry. So that's a totally big application for this kind of work. So the entire 3D movie
Yeah,
can be captured by Saint because no one can steal it, encrypt, it's encrypted. So you can bring it back compressed. So,
cool.
okay, so now we are seeing on the left and right. Basically, on the left, you're seeing points that are taken away by each sphere. Like I said, each sphere comes and takes away some points like that, takes away points like that. On the left, you're seeing more and more points removed. On the right, you're just seeing that sphere that's taking away those points. I think we use 50 spheres. So some are large spheres. It's in this case, it's random. We didn't do progressive, we just dropped the transact style, 4 points, fit a sphere, that stuff. I'll play till 50 and then maybe I should. Okay. You're seeing the reconstruction here. You did say it, now bring it back. On the right, you're seeing the points coming back. On the left, you're seeing the spheres that is giving you the points back. Right. Okay, so at 50, I'm sure you will get all the points.
I'm curious if the reconstruction can happen online, or is take a long time to do that?
It is fast. It is fast. It's on GPU. It runs on GPU. We just improved it quite a bit. Definitely under a second. The question is, can we do like 10 per second? That's what we're working on. Right. Yeah. So this picture represents centers of the spheres. For on the left 50, on the right 175. So it just gives you an understanding that the centers can actually go anywhere. It doesn't have to be behind the face, right? Remember, the points can be anything, just capture them. Each color represents a different sphere. Okay. This is, different runs. If it's random, will have different centers, but then usually we found that they are distributed similarly. So all those centers, so just different faces and showing the centers also. Okay. Like I said, more spheres. So each color represents a different sphere. Okay, so 5 spheres versus 200 spheres. You can do however many, like I said, lightweight versus heavyweight. It's not just faces. It doesn't have to be a nice, smooth surface. It can be any data. And this is the medical data, KIDS 19, it's a kidney data, 3D, manually segmented. So you can see Saint doing just fine for a volumetric kidney data like this. Again, it's the input is volume, but people have actually manually segmented it. And so you have a surface and you're creating the surface back using Saint, and it's pretty accurate. Obviously, it's qualitative. I do have numbers, but okay, so that's each sphere basically on the Saint. And the distribution of spheres for that kidney data, again, it can go anywhere. So in fact, one of the best application of this is you can probably bring out the patient's kidney by centers. So retrieval is one of the big applications, shape retrieval. So maybe the tables have certain centers and medical data. So because of the big data, they have so much data, you can retrieve things in a much efficient way using Saint, because you just have center and radius, you can index. Okay, so compression on the, so the blue picture shows the original data, okay? And the red picture shows the compressed original data by just regular GZIP. On the second one is the blue is the random Saint, and red is the Saint compressed using just regular approaches like GZIP, okay? So all you need to now check is the red one on the second and third bar compared to the red one on the first one. So you can see that that is 300 plus, and this is 150. So at least 50% is what I'm saying, at least, right? So this is the original. So that's compressed original, and that's the Saint. That's the compressed Saint. So you can see that there is a. This is probably like 300. This is probably like 150 provides. So that's guaranteed, and more can definitely happen with other interesting stuff. Okay. Also, it's scalable. You can cut down the spheres and whatnot. So we found that to be the case in all. That's the phase data. That's the kidney data. Okay. And that's the ScanNet indoor ScanNet data. I said there's indoor data out there. Okay, so that said, are we messing up with our classification and other things? Is the key, right? If you're not able to classify, what's the point? So we take that latitude and longitude, right? That theta and phi, we project it, and then we take that vector, and then we make the feature vector as a added feature vector along with XYZ. We put the center, we put the radius and this theta phi, and use that into classification. So we take the existing top classification scheme, so we add Saint. Is it getting better? Classification as in 3D classification, 3D object classification. Okay. So the model net is per object. It's done in Princeton, by the way. ScanNet is the indoor scene. Okay, so I mean, I'm not reading everything. 3D CAD models, 40 categories, 9,000 plus training, 2,000 plus test. ScanNet is a real world 3D models, 15 categories, 2,000 some training, 581 test. Okay, is indoor scenes. Now this is the example of model net. It's a wardrobe. We ran Saint on all the data, right? So each color represents different sphere. Okay. This one is example of bookshelf, example of mantle. Now we actually did original classification, top one. We added Saint features. Yeah. So you get above that value with what? With encryption, compression, everything, and get better classification.
So these require retrain of the pointnet model.
We did retraining for pointnet. So we did the test only. So that means the entire pointnet is converted into Saint, and we added this feature, and then we have a new model, and then the test one we use that feature. So we had to train it again, which is pretty fast. Yeah. So this one on scan object for structure from motion, we didn't have to train, by the way. I'll show you that result. Okay, So PointNet++, RepSurf is a pretty latest one. This PointNext is actually 2 months back. Okay, everything you see the increase. And these days you get papers with like 0.1% increase. Okay, so
You also
people,
get paper fast, 2 months later, and now it's.
Right,
1
right.
month later, somebody else.
right, that's another issue. People just come up with new ones. So these are the most latest, I 22, definitely. So there is also, okay, so one of the interesting things here is the 3D data is converted to 2D because our occupancy map is 2D. That's interesting. So we are not projecting it, but we're just somehow taking that into 2D space. So there is a particular method called multi-view classification for the same data. What they do is they render it from different viewpoint. So we said, okay, fine. We take all the viewpoints like chair, different viewpoints, and add this occupancy map, which is our 2D representation. And right, so multi-view, we add the occupancy, and we get a 0.1. Right. Okay. So we get a 0.1 increase on that. We also did, so in this PointNet approaches, there is something called farthest point where, so they don't take all the XYZ points, they take 1024 points on the data and then does PointNet on it. Okay? So obviously, there are thousands of points, they don't do all the points. Now we pick those points based on our occupancy because spheres are also representing, remember the sculpture example, spheres are representing the most important to less important. First sphere has most important, second one has next best. So we pick points based on that. And we say, okay, now how about we run it with that point selection? So here is relating to your question. So we do Saint based on this, but we only do, okay, you're not able to see the mouse, right? So this is related to your question. So here we don't need to do that for training because we're picking points. We could do it on test. So we only did it for test. Okay. Here we did both training and test. So every time we see that things are improving. So this is the 90.7. If only test, it's 0.1. If both training and test, it's this much. I just want to, yeah, I'm glad you asked. People do all kinds of stuff, they add normals and everything, but no matter what, we add Saint and it increases the classification. So why this is important? Because you can run it on mobile phone. If it is this points, then you can write on mobile phone, right? So this stuff is important because if it's improving on these number of points, for example, from here to here is 0.3, it does mean a lot. On a cell phone, you are getting all this additional performance.
I'm just curious, when you say it does improve a lot, so in terms of how, 0.3 improvement,
Right.
that the eyes will see a big difference, or?
So that means some are being classified correctly.
Oh, okay. Like a face recognition, okay, maybe you will do it.
Right. The model net, for example, has all those objects. Maybe in some cases, the wardrobe is being confused by mantle before, but by adding Saint, it's doing it correct.
Okay.
So that's true. So So then we also went on to another classification network, and then we said, okay, how does it work with different spheres? So you can see that more spheres is helpful. Obviously, after certain point, it's not helpful. So we always pick the right one based on the computation.
So why is this? So I thought you get the more is better.
Which one is more?
I mean, number of spheres, keeping increasing.
For reconstruction, yes.
Here, after 50, something like that, you are
True, because it's overloaded.
overloaded.
Right. That means the features are not helping. But so the beyond 50, those spheres between two objects are coming to be the same, maybe.
Okay.
And it's confusing rather than distinguishing.
Okay.
A good question. Right? Why is it happening? That's a very good question. In fact, it would be nice to actually go back to some objects to see.
Well, then, so the next potentially is how do you find it optimize the one for
Right.
this particular
Right.
thing?
And this is for model net, and for some other data set, it will be different.
It's very different.
Right. So in vision, everyone talks about model net scanner. In fact, we came up with a new one recently. We should check these things.
Okay.
So great. So in vision, the main tasks are, like I said, localization and so forth, classification, and also reconstruction. So you want to find the depth. The depth finding in the previous slide, we saw CT and depth scanners, LiDAR, but there is also an approach called structure from motion in computer vision, where you can see series of images, track the series of images like stereo, and then use those tracks to find out the 3D. Just like monocular vision, someone with one eye is able to tell a little bit of shape of the objects like that. That's called structure from motion. So we use Saint in the structure from motion. So what I meant is you don't have multiple images. I mean, you don't have multiple views, but you just have a camera with the object moving and you estimate the depth. That's called structure from motion. It's a classic approach. So basically, these are the indoor scenes. That's the depth obtained by this structure from motion. Again, it's right. We're not given depth. We created the depth based on our network. Right? So we came up with a loss function based on Saint. And we did experiments with that loss function onto an existing network. And that's where you can see some RMS error, where you're seeing the Saint depth is error of the Saint depth is much lesser than the other. So these are the errors compared to the ground truth. But this would reduce the error according to the ground truth. Is that clear?
Or this one, actually, you are using RMSE, so the lower is better.
Lower is better, yeah.
Okay, now you want to reduce the
Right.
0 point something.
So yeah, so you asked about reconstruction error, but this is structure from motion error. But reconstruction error, we saw it qualitatively, but we can also easily do quantitative. So yes, this is estimating structure from series of images given, like video. And they have a ground truth because they can do connect. And then they rotate the object or something and use the video to get structure from motion, right? So then you compare it with the ground truth. So for example, that's the famous one. So these ones have given this much and that's reduced. Yeah. So the kind of data is like this. So you get input is on the left, output is on the right. Okay.
So the right side, it looks like a
Depth.
thermal image.
Yeah, I know it does, but that's basically colors representing the depth.
The depth, okay. So how do you understand it? Can this be applied to the thermal image? Like infrared image?
That actually thermal image also you can use it for depth computation. In fact, we do that in our lab. So if you do thermal image, then you are finding the shape of something that's hidden.
That's the way.
Right.
Because
We do that.
we just have a paper accepted by Nature Scientific Data.
Mhm.
So it's showing that using drones to use the infrared image, taking a lot of on the.
That's
top.
good.
Yeah, I know. I thought about you.
That's
because I should share that data to you. So that
Yeah,
it's on the high level. We can detect if there's somebody is there.
right on,
That-
right on. That's very interesting to us.
Good, good. Yeah, we have that data set.
That's great. That's great. Thank you. So if something is in a bush or something, thermal can see through it, and then you structure from motion do that. But you can do it with LiDAR because LiDAR, bushes will obstruct.
Yeah.
That's a great application for here.
Okay.
So right. Okay. So the depth map is on the right. Left is the input. Like I said, the Saint is improving the SFM result on the right. So at this point, I just want to show. There's a student in our lab who takes this depth maps and then finds out new mechanisms to classify objects. For example, in the PointNet model, they take a ball query, whereas he came up with this ellipsoid-based query to understand this better. He's graduating, so you're welcome to attend the invitation. So this just shows what else we are doing in our lab, which improves the networks from different methods that are existing to interesting and novel methods at the architectural level. So for example, with his method, the accuracy from 90.7 can go to really high by at least 1% using this kind of ellipsoid query. because again, that 1024 points I talked about, when you do this ball query, you can pick points from each ball, but you can use the ellipsoid to use points. I'm basically showing an interesting data set here. Our application is not just for regular vision, but for imperfect vision. What if your pictures are not perfect? What if your image is not perfect? Our goal is for a visually impaired person or someone with weak vision to be able to go to a grocery store and be able to purchase things based on their iPhone captures. We have collected the largest grocery set out there. We are right now in the process of publishing it. We actually went to all the Acme stores out there in Delaware. It's Delaware small. We went to all of them, collected this data. It has 38 categories of packages, 34 categories of fruits, total 100 categories of course, and 28 categories of vegetables. You're talking visible and LiDAR data, depth data. So because we have this point cloud-based analysis, so all of this data is there, and we're obviously waiting for publication before we open it up. So it's the topmost grocery data out there. Okay, so you're talking about data like this, where someone had taken a picture, they're looking for oranges. Obviously, we're talking about weekly visually vision. The computer is supposed to tell oranges are here on the left, and it's telling you based on not just texture, but also the depth, because we work on this. So of course, they will be looking at some of these packages, whatever that they are looking. With this 3D data, we like to give them pointers as to which direction to go to pick that item.
This could be very helpful for the robots.
Right.
The human, because we already much faster than this. I can find it.
Right.
But for robots to go there and pick up stuff, they will be benefited a lot, because several of them are working on this autonomous mobile robots.
That would be great if we can collaborate with those.
Yeah, that would be helping for the people, the guiding.
They don't even have to go. They can just wait until the robot brings and picks up.
Yeah.
Right.
So people, when the eye see, you see recently how this, when the US hit the balloon, hit the balloon, so basically that the missile using the approach is similar. So when the pilot stop the balloon, then push the button, then they can go. So I think we can do something similar. So if I'm watching that apple, little robot go there, grab it.
Right. That's a great idea.
Yeah, that is exactly what we call assistive, using robot to help the people to move around.
Right. It makes perfect sense. Yeah, that'll be great.
Okay. Yeah.
So there's a new topic in the computer vision called neural radiance, where one can actually get 3D from structure from motion kind of data. We're also working on that area where we take that kind of scene, we segment out the oranges. We also bring out the 3D of those oranges automatically. And we use all this back into hopefully Saint representation because there's going to be humongous data. So you need to represent that compactly and encrypt them and still help the classification and everything else. So that's the goal of our pipeline. So that said, we are interested in imperfect vision, a vision where your camera, cameras are not perfect, your view angle is not perfect, but still also multimodal, like we said, infrared and other ways to actually detect what you need rather than what's on the outside. So that's great. So evaluating Saint on semantic segmentation, we did classification, but not quite on segmentation yet. On the object detection, the first picture of the point pillars. Retrieval, like I said, radii and centers could be used to retrieve objects. We also can add more interesting. So curvature has a total different meaning for Saint because you have a sphere, but that sphere is capturing this point and this point. So Saint curvature is different from real curvature, but then that could be helpful for classification. So these are things that we're very interested to kind of continue on. Okay. Thank you for your attention very much. I'll be happy to take any questions.
Thank you. So we can take questions from the in-person first, then we can ask the people live.
Yeah, I have a to the parameters that you mentioned, like the number of the severe and severe hacking manners mentioned in the Euclidean.
Could you packing mans, which one?
Sphere of hacking.
Severe part.
Oh, yes.
I think those three are kind of the parameters may have some impacts related to the compression and.
Right. Right.
So in terms of the dynamic scenario, application scenario, like the how do you choose the optimal value for those kind of the parameters?
Right. So, yeah, that's a good question. That's a great question. So what did I stop the share? Okay, I'll just do it. So in this scenario, is it okay now, right on the screen? Okay. In this scenario, if we have lightweight, we could actually make the number of spheres to be the first layer, just make it like 5 or 10. Lightweight, as in if you're talking about mobile-based computation. But if reconstruction, if your object needs to look realistic, like medical application, you don't want to miss out on any point, then you want to have the maximum. Now, how much maximum is the question? In that picture ablation study, you saw beyond 50, we are cutting down on accuracy. So we found 50 to be optimum, but of course, that's just a number empirically derived. We need to, so there is actually, so sphere packing is one way to find out the number of spheres required for a scene. And we are in the process of theoretically finding it. Like, how do you theoretically find out how many spheres you need? And I think that's a great point you're bringing up. The other thing is, however many spheres you do, the rest could just be added as XYZ. That way you don't lose anything. So that's also an approach that we were thinking about. So that means take all the spheres, the rest, if you want every accuracy you want, keep the XYZs that are remaining. But essentially, there is no theoretical derivation. We haven't gotten into it yet as to the number of spheres required. But yeah, but the point I just want to add that the point I'm trying to make is that maybe you don't need all of them if it is classification. Remember the sculpture Spock example. The whole idea is what is needed, what is not needed. Thank you. Yes.
Quick question. So could you please go back to the evaluation you just gave us, the accuracy and the number of spheres? Yeah, I saw there is the peak point and there is just a slight decrease in your chat. So my question is, if I apply this in the application, so how you can determine the numbers of spheres, because I guess while we check the peak point, so do you mean we just meet the overfitting of the?
So let's look at the slides. I think you meant this one.
Yes.
Okay. Okay. So were you saying use this curve to find out spheres, or could you repeat your question?
Yeah. So I mean, does the peak point means if there is a slight decrease, so that means the number of spheres is more than 50, so there is a slight overfitting.
Right. So like I said, I think maybe beyond 50, it's getting more confused between different objects.
Yeah. So
It's possible because if you have planar surfaces, for example, then any object, if you run Saint, you may get the same center for different objects because it's plane, and then it's confusing. Bottom line, beyond certain point, it's not helping. Finding out that point theoretically is something we haven't done.
okay, so if I apply this in an application, so do you guess more spheres can be better, because sometimes in the actual reality, so maybe there should be some confuse in our reality, but yeah.
So obviously, computational resources is the key. If I have a mobile phone lightweight and stay here. Also, if it's classification, maybe I can just stay here.
Oh, sure.
But if it's reconstruction, like medical medical surgery. So that's a big thing because a lot of experts are geographically distributed. And the expertise time is very valuable. They may only spend like 6 minutes on a surgery by looking, but they want high accurate data. So for something like that, this curve don't have any meaning. You just go as much to basically say, okay, this is the data. The kidney data, you want to send it to a surgeon who's an expert looking for something, tumor. You want the most accurate, so maybe 175 spheres. Also, it depends on, so that's a different application where accuracy matters. Also, it depends on processing. So you're converting data into, the difference between the data compression is nothing but processing time. You're fitting spheres that you're condensing the data, but you're processing time. So if you have more processing, no one can stop you from going more spheres. So we are working on more parallel strategies. It is all GPU right now, but still some more parallelization maybe could happen to make it real time. Like I said, we are under 1 second right now, but more seconds is more frames per second is better. Basically, LiDAR generates, let's say 3 to 5. It should match it up, I think. Okay.
Yeah, I want to follow up on this. So it's like in deep learning, they usually build a so-called feature pyramid network, which takes different layer of the feature, some of the deeper feature, some of the from the lower layer, and then they combine them together to do some applications. I'm curious if that can also be applied to this scenario.
Right.
Sometimes the deeper feature can be removed, but it's not
Necessary.
necessary.
For a given task. Right.
Yes.
Right. So that's the kinds of stuff we are interested. So it's unsupervised right now. So, like I said, for classification, less spheres. For structure recovery, more spheres. But a generalization in terms of an equation is not there yet. Sphere packing is the only connection we could do to the math behind this whole thing, right? So we should do a little bit beyond where if we have an equation of some sort where I have points and then that equation tells me how many spheres. Maybe I should just train. I should just train so that I load up the points, number of points, and somehow my system will tell how many spheres to use. But I like your idea that it should be some kind of a hierarchy where there is deep ones for more spheres maybe, and coarse ones for less spheres, and do a best job of classification and whatnot. Thank you.
Okay. Do we have any questions from audience? No? Okay, I think that's good. Thank you so much. Let's thank our speaker. I learned a lot because it's a very different area from what we are doing. So thank you.
A lot of collaboration points.
Yes. Yeah. Cool. Thank you. The data center you guys generated 3D stuff. You created yourself, right? Then why not you call the UD something? Because I saw NYU something. This is a good.
Okay.
Yeah, you can if you this will be help to boost our